computer. All right, so let me go here and share my screen. Before I do that, today's lecture 9, I believe. Okay, so let me just make sure we have lecture 9. Oops, just a second. Okay, this is a little bit bizarre. Okay, well, anyway, let me open it up here and do this. Okay, so share screen. iPhone, iPad. Okay, here, goes here, here. It's a little bit slow today. All right. Okay, all right. So here we are. This is the T-beam design. Okay, now, first of all, lecture 9, T-beam. Okay, so let's take a look at T-beam, right? What is T-beam? So objective 1, stress distribution in T-beam. Okay, so this is the main difference between a T-beam and rectangular beam is the internal stress distribution. All right, and then second is example to show how to design a T-beam. Okay, so these are our objectives. All right, so first of all, let's take a look at T-beam. So 9.1, stress distribution in T-beam. Stress distribution in T-beam. Sorry, my writing is a little bit chicken claw, so I'll try to write it as organized as I can. Okay, so say I have a T-beam looks like this, right? Regularly, it just have a shoulder on the top and have a rectangular portion at the bottom here. And we call this flange, by the way, right? This is the flange of the T-beam. So since it's flange, we have a width, okay, width of the flange. Usually we call it BE because this is effective width, okay? BE is the effective width. Okay, let me just write down here. So BE is effective width. And why we call it effective width is because normally, normally we have a design like this, right? This is the cross section, and we have a continuous portion, and then we have a rectangular part girdle underneath it, right? So we need to define a width, right, to cut it so we can design them individually. So this is called effective width. All right. Now we're not going to get into this today. We'll talk about next lecture, which is Thursday. But keep in mind that this width you have to pick on yourself, right? You have to pick this number yourself. Okay. So with that, we have also the height of the flange. We call it HF. Height of the flange, HF. And we have a width of the bottom rectangular part. We call BW, the web. BW is the web. Okay. So that's the web width. All right, and also we still have the height. Okay, and if we have bars, we also have the depths. Okay, so this is the geometry. This is the geometry of our T-beam, right? This is the geometry of our T-beam. Okay, now given this is a geometry, right? What will be the stress look like, right? What will be the stress look like? Now comparing to the rectangular beam, right? Just quickly remind us for rectangular section. For rectangular section, say I have the reinforcement at the bottom here, and I draw a strain diagram. This is epsilon Cu 0.003. Again, this is epsilon S. And the internal stress looks like a Whitney stress block. Right? This is 0.85 F prime C, right? And this is a tension, so Fy typically, right? That is the normal stress distribution. So this is always what we have shown so far, but let's take a look at the 3D view, right? Just to take a look at the 3D view, right? So from the side, if I have the section look like this, I have a section look like this. Right, that is the rectangular section, and if this is the B width, so this is the B width. Okay, now, and we have height, just in mind, keep in mind, this is the height, right? We have the height. Okay, so if I use red to draw the stress distribution, right? To draw the stress distribution, right? So you see that it is more like a volume. It is more like a volume. Okay, and this distance here is 0.85 F prime C. Okay, 0.85 F prime C. Right, it's like a volume. So you see this, sorry, you see these needles all over the place, right? You see this compressive stresses in this small block. Okay, and we also know that this height right here is A. Right, so that is the compressive stress. And for the tension, so I extend right here, and let me use different colors of blue, and this is the tension. So it's relatively long, okay, and this is Fy. Okay, this is Fy, right? So this is a 3D view of the stress distribution. 3D view of the stress distribution. Okay, now take a look at the T section, right? Take a look at the T section. So I have a T section right here. Right, same geometry description we had before. This is height of flange, effective width BE, effective width of the web BW, right? Reinforced on the bottom here, AS, and the strain distribution same as before. Okay, same as before. Now this is epsilon CU 0.003. This is epsilon S, which in this case should be epsilon. Sorry, should be bigger than epsilon Y, which is yield strain. And now the Whitney stress block, the Whitney stress block. Now this is a little bit interesting. Why is that? It's because I have flange now, right? I have flange now. So naturally, you see that my stress distribution is a little bit more complex. It's a little bit more complex. Okay, so I have actually two regions right now. So there are two possible scenarios. There are two possible scenarios, right? So let me go ahead, just write down, show the Whitney stress block first. Okay, show the Whitney stress block first. And this is 0.85 F prime C. And this is A. Again, right? This is yield stress Fy. Okay. Now be careful, pay attention, right? Pay attention, be careful now, right? So there are two scenarios. So let me just move this thing stuff on the left a little bit so I have more room to play with. Okay, and to make it symmetric so you can compare. So let me just draw this thing here and a little bit here. Okay, so I have two scenarios. First, if, now this is HF, right? This is HF. Apparently my A is a little bit too big, so let me just reduce that a little bit, right? Say if I have an A that is just within the flange. Okay, so I call it scenario 1, right? So let's just say scenario number 1. Scenario 1, that A happened to be smaller or equal than HF. Smaller than equal than HF, right? If A is smaller than equal than HF. Okay, that means my compressive zone is within the flange. My compressive zone is within the flange, right? So if in that case, Justin, Mr. Heckman. Hello.
Yes.
Hey, how are you, buddy?
Hey,
Can you
Bob.
hear me? Hey, good. So quick question here, sir. So if my compressive zone is smaller
Can
than
you hear
the,
me?
yeah, I can hear you now. Can you hear us? Can you hear me? Justin? You there? All right, well, I have a one Okay, school internet. Okay. All right. I have one problem with Justin. Okay. Well, let me try my next victim then, Justin. JD, Mr. Crawford. Hello, Mr. Crawford.
Yeah, I can hear you.
All right, good deal. So at least I have one that is working for now. Okay. All right. So JD, quick question here. Say if the compressive zone is within the flange, okay? If the compressive zone within the flange, right? And I want to draw the 3D stress distribution. Will there be any difference for a T-beam or for rectangular beam in that case?
I'd say there'd probably be more reinforcement from compression in the T-beam, just because you have more concrete in the cross section right there.
Right, right. That's a good answer. In other words, is if I have a compressive zone that within the flange, so essentially I can treat the T-beam as a very wide rectangular beam, isn't it? Right, JD?
Oh yeah, yeah.
Okay, that makes sense. Thanks a lot. All right, just make sure we're paying attention, right? So that is to say, if I have my compressive zone within the flange, might as well treat my beam as a wide my wide rectangular beam, right? So I'm going to use my B effective as the width of the structure, right? As the width of the structure. So in that sense, the tension is still here. Tension is still here. Now we're just going to say this is AS and this is the tension. But the concrete compression now I can write down C would equal to 0.85 F prime C. And this will be B, E, and A. Okay, B, E, and A. Okay, so that's the first scenario. Now the second scenario, right? Scenario 2. Now I have still the T-beam, right? But in this case, right? In this case, so happen to be that my compressive zone is bigger. My compressive zone is bigger than the HF, right? So try to adjust here. My drawing is horrible. So my compressive zone A is bigger than HF. Okay, so in this case now I have a little bit awkward situation. Why is that? Is my stress is no longer uniform. Okay, I need to actually divide the section into two parts, the flange and the web. Okay, so I have to notice that in this case the stress distribution is not uniform. Okay, it's not uniform. Okay, so if it's not uniform, what does it look like, right? What does it look like, right? So let me show up the scenario a little bit more. So scenario number 2 is zoom in, right? To explain why the stress distribution is a little bit. So if I says, okay, now I have a compressive zone that is bigger than the HF. So I can go ahead, divide the section into two parts. And one is called the flange part, right? And the other is called the web part. So this whole section now equal to two parts added together. So I have now just the flange portion. Okay, I'm gonna use dash line for the web. Okay, and plus just the web portion. Use the dash line for flange. Okay, so we're going to treat them separately. We're going to treat them separately and add them up together later, right? Add them up later. So let's take a look at the flange. Let's take a look at flange. So if I only have the flange, right? So I'm gonna see in the section like this. Okay, this is the flange here, and this is the flange here. Okay, and the middle web, just gonna ignore it. They're there, but for now, just ignore it. Okay, now for this case, we're gonna assume the stress in the flange, right? We're going to assume the stress in the flange are all 0.85 prime C. So it's like a cube. It's like a cube. okay, with the same width, that is 0.85 F prime C. Okay, 0.85 F prime C. Same thing here, okay, 0.85 F prime C. So that is, say, if I want to divide my compression from the concrete into two parts, divide my compression from the concrete in two parts, I have, this is called the concrete CC flange. Okay, CC flange, right? That is equal to 0.85 F prime C, and this is A. Now, what is my A? This is basically HF, the height of the flange. Okay, and then B, in terms of width, now what is the width? The width right here is what? Is BE minus BW. Okay, this is BE, we minus, and this is BW. Right? So this, right, this right now is the concrete compressive forces, right, from the flange only, Okay, so with that, I can actually compute the required reinforcement for this, because I can call it AS, right, AS1 or ASF flange equal to CC flange. Okay, so that means ASFY equal to 0.85 F prime C HF, which is the height of flange, and BE minus BW. Okay, so ASF equal to 0.85 F prime C HF BE minus BW divided by FY. Okay, so this is the required reinforcement for flange. Okay, I can even go further. I say, okay, now I know I can compute the moment resistance come from the flange. The moment resistance come from the flange. So that is MNF equal to ASFY multiplied by this is tension, by the way, so TF, right? Tension from the flange. And this tension, right, TF, need to multiply distance, okay? Just mark it here. So this is my bar. Just put two bars here as an example. This is my bar. I need a distance from the bar to the centroid of the compression, right? To the centroid of the compression. Now I know this is uniform. So the centroid, let me use a different color here, must be at some distance, right? Which means it must be in the middle of it. So this is HF divided by 2, right? HF divided by 2 away from the top. Okay. Now the depth, right, is right here. So what is the distance between the tension and compression? Right? That is D minus HF divided by 2. Right? So now coming back here, I know the moment here should be multiplied distance D minus HF divided by 2. Okay, and just to clear, I can remove this. And this is what we call the moment caused by flange. Right? So this is moment resistance from flange. Right? So that is the contribution from the flange, right? So we're still under scenario number 2, but component from the flange, right? So this is scenario number 2, this is from flange. How about from web? Right? So take a look at the web now. So the web is basically another rectangular section without the wings, without the flanges, right? So I can treat it just like a rectangular section, So when I draw it, I draw like this. So this is my dashed line, which is the flange. Right? I still have them, but ignored. Okay, but the solid part is the web part. They're still here. Okay, that's the web, and I have bars here. And keep in mind, right, these bars, right, that's the reinforcement needed for the flange, and these bars are the reinforcement needed for the web. Okay, ASF means flange, ASW means web. Okay, they're different. They're different. So now I have the Winnie stress block just exerting on the solid portion, which is the web. Okay, and it's uniform distribute like this now within the web. Within the web. Okay, so this is 0.85 F prime C. My horrible write-up. Let me change that. 0.85 F prime C. Okay, and the height of it is, what is the height now? Okay, what is the height now? Right, so we need to know the height of this. We need to know the height of this. Right, so we'll say if the flange, right, is the whole HF, is the whole HF. Okay, so we have to actually determine this effective compressive zone, right? So just call it A for now. Let's just call it A for now. Okay, so for that, I will get the compression. I'll get the compression. Let me just divide it so you don't confuse. Get the compression from the web CC W, okay, equal to 0.85 F prime C, this fellow right here, and multiply with the height A, and now I need a width, and now this width is BW. So width is BW. Okay, so this is a compression from the web, Now to balance this, tension equal to compression, right? So tension, this is from web, equal to compression from the web. So ASW, right, Fy equal to 0.85 F prime C ABW. Okay, so the moment resistance then from the web, right, equal to ASFY, ASWFY, which is tension, right? And draw it again, the total compression is right here, CC, W, and the tension is right here, and the distance between them two is D minus half A, right? We've seen this before. So, so I have, this is D minus half A. Okay, so this is the contribution from the web. Okay, and don't forget, right, I can get my A from this equation, which is ASWFY divided by 0.85 F prime C BW. Okay, all right, so with these two components, the flange and the web, right, with these two components, right, all we want to do is this. We want to make sure that the MNF flange plus MN web, okay, and phi reduction factor in front of it, right, it has to be bigger than equal than, the design MU. Design MU. All right. Now, quick question here. Okay, I'm gonna pick my next victim. Lucas, Mr. Girk. Lucas.
Yeah.
Hey, how are you doing, buddy?
Doing pretty good. How you doing?
Not too bad. So here, for the stress reduction factor, right? For the stress reduction factor phi here, do you think they will be the same for both MNF or MN web, or they'll be different? In other words, am I writing? Is this writing correct? You know, should I have a common phi for both of them, or should I write them separately?
I think it should be separate
Why?
because like one of them's a depth to the isn't like depth fees based off depth to the steel.
Yes.
So it would be different for webs and if there's not steel in it, right?
Okay. Think again. Well, the logic is almost right, but there's just a tiny mistake there. Think about it, right? So how we determine phi, again, how we determine phi, that is determined by the last row of steel, isn't it?
Yeah.
So that is called epsilon T, right?
Yeah.
And epsilon T is determined by dt, isn't it?
Yeah.
So for the last row of steel, right? For both sections, they're the same section, right? They're eventually the same section, right?
Yeah.
So they have the same
Phi.
phi, correct, right?
Yep.
Right, great, thanks. So be careful, okay, common mistake. They have to have the same phi here, okay? All right, so this is the design. Sorry, this is an analysis of a T-beam. This is analysis of T-beam. Okay, which is not too bad. Which is not too bad to calculate. All right, so I'm going to walk you through with a simple design problem to get a flavor of it. But before we start, okay, what we're gonna do is this: establish a procedure first. Let's establish a procedure first. Okay, so given this is the analysis process, okay, what we do. All right, first, okay, estimate the compressive zone A. Okay, estimate the compressive zone A. Okay, how to estimate that, right? So A equal to AS Fy, okay, divided by 0.85 F prime C B E, okay? This is effective width. Okay, effective width. All right, so if A is smaller than the flange height, is smaller or equal than the flange height, okay, then design as a rectangular section. With an effective width BE. Okay. Now, if sorry, if A is bigger than HF, okay, then design as T section. That means separate the flange from the web. Okay, separate the flange from the web. Okay, so this is the general concept. All right, so let's take a look at an example, okay? Let's take a look at an example. So 9.2, an example, right? On T-beam design. Okay, all right, so now let's take a look at T-beam. So a T-beam is given. I gave you a geometry. Okay, now be careful though, before I forgot. When we say we design a T-beam, that is designed for reinforcement, okay? Normally, the geometry is given for T-beam, so you don't have to worry about the geometry, okay? For singular reinforced section, we covered how to design with unknown section. But for both AA and T-beam, we only require us to learn how to design the reinforcement, meaning the geometry are almost given every time, okay? Every time. So this is for known section, okay? Known section. All right, okay, so let's get back to the geometry. So I have a T-beam, and I tell you that the width of it is 47 inches. Which is given, okay? And I have a width, BW here, very odd number, 11 inches, okay? And I don't know how much steel I have, okay? I don't know how much steel I have. I have a depth of fixed 20 inches. And I have a flange that is fixed as well, 3 inches. So this gives me the distance between the edge of the flange, the bottom right here, this is 20 inches. Okay, in other words, H is 23 inches. Okay, all right. So this is my geometry. This is my geometry. All right. Okay, and I'm gonna go a little bit on lower strengths, right? I'm gonna go a little bit low strengths, right? I would say for now the concrete is say 3 KSI. So F prime C, let's use 3 KSI. Very low strengths, very low strengths. And be careful, we have to use a different beta 1 number, right? We have to use beta 1 number. And you later realize that we don't need it. We don't need it, okay? For this design, we don't need it yet. Okay, so let's just say now I use grade 60, GR 60. So the yield strength Fy 60 KSI. Okay. So the whole purpose, right? Whole purpose of this design. Let me just put this out here so you can see it better. Okay. So the whole purpose of design is to make sure that design for AS to make sure that phi mn is bigger than greater than mu. Okay. So we need a mu, right? We need a applied moment. We need applied moment. Okay. So I'm gonna say I need mu that is 533 kipfoot. Okay. So this is the problem. This is the problem. So I'm gonna start a design, right? So start design. So solve. First step. Okay. First step is to estimate the effective compressive zone A. Okay, effective compressive zone A. But to estimate effective compressive zone A, I need to know the area of steel. I need to know the area of steel. So I have to do assume. So I have to estimate required area first. How to do that, right? So I'm going to assume first phi equal to 0.9 tension control. This is assumption right now, okay? And because I want to satisfy phi mn bigger than mu, okay? So I'm going to assume we'll start design as something, a rectangular section, right? As a rectangular section. So I have AS required, okay? AS required equal to mu phi, okay, of y d minus half a, okay? Assume rectangular section. Okay, so mu right here, and I need phi, which is 0.9, fine. Fy is here, fine. But I don't know the depths. I don't know the A. Sorry, I know the depths, but I don't know the A. So I don't know this distance. Okay, so for all we know right now, we can assume the distance is JD, okay, and let JD equal to about 95% of D. 95% of D. Okay, 95% of D. That is the assumed distance between tension and compression. Okay, assumed distance between the tension and compression. Okay, so let's carry out the calculation. So from this, the AS required then, AS required, sometimes I forgot D here, required then is 533 kipfoot divided by phi, we know, we assume to be 0.9, Fy 60 KSI, and JD we said 95% of 20D, right? So this is 0.95 divided by 20 inches. Okay, so 20 inches. Okay, now be careful. This is different from the rectangular beam, okay? Different from rectangular beam a little bit. Why is that? Because JD, recall, for rectangular beam is 0.9D. Okay, so this is for TB. Okay, again, let me put this thing down a little bit.
Hey, Bob.
Yes. Yes, sir. What's up?
Do we need to take the top 533 and multiply it by 12 to get an
Oh,
inch?
yeah. Just bear with me a second. I forgot. Thanks. Okay. So here, let me convert that to be 12 inch per foot, right? Okay. So that's what we have. Okay. Now, run through the calculation. I have 6.24 inch squared. And now that is required steel. Requires steel. Okay, and keep in mind that the whole exercise, the estimate, is to estimate the compressive zone A. Okay, the whole exercise estimate compressive zone A. Okay, and this is assume, this is under the assumption that my compressive zone A is within the flange. Okay, this is assume that I'm going to use BE. Okay, I'm going to use BE to estimate A. Okay, so with this, I'm saying A will equal to ASFY, AS required, FY, divided by 0.85 F prime C, okay, BE. Okay, so run the number, AS requires 6.24 inch squared, FY 60 KSI, divided by 0.85 F prime C, 3 KSI, and 47 inches. Okay, and then I got this number to be 3.12 inches, which comparing to the HF is bigger. It's bigger. Okay, so this means cannot be designed as rectangular beam. Cannot be designed as rectangular beam. All right, so this means we go to scenario number 2, right? Scenario number 2, recall scenario number 2. We have to separate the beams, right? Recall we have to do this equal to this, right? Plus, oops, sorry, hey, there's no line here, plus this. We have to separate, right? In terms of flange, in terms of web. Okay, so with that, color it up. We have to do a difference. So for flange, right? For the flange, right here for the flange, right? We know that Fy or ASF, Fy, tension side equal to 0.85 F prime C, and BE, this is BE here, okay? And this is BW here. Minus BW, that is BF, and then HF. Okay, so with this, ASF then equal to 0.85 F prime C BE minus BW HF divided by Fy. Okay, so I run the numbers, and this is ASF equal to, on the top here, 0.83 multiplied by 3 KSI multiplied by 47 inches minus 11 inches, okay, and multiplied by 3 inches divided by 60 KSI. Okay, I save all the units because everything is in terms of KSI and inches. Okay, so I got ASF equal to a 4.59 inch squared. So that is the steel from the flange. That is the steel from the flange. So I carry on and MN, okay, from the flange, then equal to ASFY, right? This is the steel for the flange, and this is tension in the flange section, D minus HF divided by 2, D minus HF divided by 2. So I bring the number in 4.59 inch squared, okay, 60 KSI, okay, multiplied by D, which is 20 inches, HF 3 inches divided by 2. Okay, so MN flange eventually equal to a 424.6 kip foot. Okay, so that is the moment resistance provided by the flange. Is this enough? Is this adequate? Apparently not, because we know mu equal to 533 kip foot. Okay, so we know we need extra moment resistance from the web, and that equal to phi web equal mu minus phi mn flange. So that brings the number in 533 minus 0.9 multiplied by 424.6. I have VMN web equal to a calculations at 150.9 cubic feet. So that means I need additional 150.9 cubic foot, 150.9 cubic foot for the web. Okay, so coming back to the web, I need to redesign my web, right? So for the web, okay, I need to treat it like this, just rectangular section, and this is width of the web. The flange there, but I ignore it. And I have a compressive zone right here. Okay, and this is A. Right? So how do I design that? Okay, this is a little bit easier, right? I'm just gonna treat, right? I know VMN web equal to 150.9 cubic foot. Okay, and this is actually equal to the ASW, the reinforcement from web, multiplied by the yield strength Fy, and bracket inside this D minus half A. D minus half A. Now, pay attention. We have a rectangular beam here, essentially, right? This is essentially a rectangular beam. So to estimate the distance, the lever arm, basically, between the compression and tension, JD for rectangular beam is 0.9 D, 90% of depth, okay? It's now 0.95, okay? Because right here, we said it, right? So 0.9 D for rectangular, 0.95 for the flange of the T-beam, okay? All right, so with this, I can carry on, right, to calculate my required steel. So ASW or AS web, right, equal to VMN, okay, web, divided by Fy, JD, right? JD we said 0.9 D, basically. Okay, so you bring the number in. So this is 150.9, okay, cubic foot.
Hey, Bob,
Yes,
I have a question.
go ahead.
Do we need to take the phi out? Because isn't the equation just for mn rather than?
Yeah, wait, just a second, right? Hold on just a second, right? So I do have to take the phi out, I think. So right here, this is phi, and then this is 0.9. So right here, I just realized that. So cancel that. So phi should be here. And then I have that, and this should be divided by 0.9. Make sense now?
Yes, thank you.
Yeah, sure, thanks. Hold on, so yeah, here's 0.9, a depth of 20 inches. Okay, all right, so I got this number approximately equal to a 1.86 inch. Okay, actually 1.9 inch. Okay, so that is the required steel for the web. All right, required steel for the web. Okay, so with this, I'm just gonna assume A equal to AS web or ASW multiplied by Fy divided by 0.85 F prime C BW. Okay, I bring the number in, so this is about 1.9 inch. Okay, 60 KSI. Sorry, 60 KSI divided by 0.85, 3 KSI, concrete low strength, and BW is 11 inches. I got A approximately equal to 4 inch. In here, you can double check that is actually bigger than HF equal to 3 inch. So we're okay. Okay, why we're saying we're okay? We're indeed designing a T-beam. Okay, all right, okay. So the next step, right? Essentially is that AS require, okay, equal to a ASF plus ASW. Okay, that is 1.9 inch squared. Sorry, there's a square there. Okay, too much detail here. Plus the web plus the flange. Or what is my flange? This is the flange. Okay, 4.59 inch squared. 4.59 inch squared. Okay, approximately, because this is 2, this is 4.6, so 6.6 inch squared. Okay, and that is the provided reinforcement for the T-beam, for the P-beam. Okay, and what we do next after this, we select the bars and run analysis again to make sure the moment capacity that Vmn is bigger than or equal to mu. Okay, which we'll carry on for the next time, all right? Thursday. Okay. Sorry, we were a little bit fast today, but I just want to show you the whole picture of how we go about T-beam, okay? So it's a little bit long today, but essentially you divide the T-beam into two parts, the flange and the web, the flange and the web. And when you design it, right, you take out the moment resistance from the flange first. You take out the moment resistance from the flange first, estimate how much needed for the web, and you go on design the web. Now, if you're lucky, that your compressor zone is within the flange, then just treat it as a rectangular beam. Just treat it as a rectangular beam. Okay. All right. My time's up today, so I'm gonna stop sharing and stop recording. But